In this mini lecture, I'm going to look a little bit at the topic of volumes of solids of revolution, and one particular method we can use to find those volumes that results in either a disk or a washer that we find the volume of in order to find the overall volume of the solid. So to get this three-dimensional solid, we start with a region in the xy plane. So maybe I have this curve here, y equals f of x, this blue curve, and considering this between x equals a and x equals b. And so we've got those lines, and then we've got the x-axis, which is the line y equals 0. So I've got this region, here, that red region, and I want to know what would happen if I rotate that about the x-axis. So if we rotate that about the x-axis, we would get this sort of solid here, right? So we've got the curve up there that gets reflected down below, and as that gets rotated, we sort of get circular cross sections as we would go across that solid, and so that's the task, is to find the volume of this solid here. The way we do that is we imagine taking this interval from A to B, and we subdivide it into a bunch of little subintervals, and each of those subintervals then has a width delta x. So you see this rectangle right here. So just like we did when we were finding areas, we can imagine a bunch of little rectangles sort of marching across this interval from A to B. And this is one of the rectangles we might have. It has a width delta x. Now, when that rectangle gets rotated, again about this line y equals 0, the x-axis, well, that one rectangle actually forms a disk. So the rectangle is still in there, but when it gets rotated, we get this circular disk from that rectangle. And that disk then, it's got, on each side, it's really a circle. Those are circular cross sections, and then it's got this little thickness delta x. So the volume of one of those disks is just going to be the area of one of the faces of the disk times the thickness, which is delta x. So that's this a times delta x. But the area is just going to be, that's the area of a circle, so that's pi r squared times delta x. And the radius then is this distance that's the height of the rectangle, essentially. So if I have this, we had this funny thing before, and it's still here, this x sub I star. Remember, x sub I star is just one of the x coordinates in this subinterval. And f of x sub I star then would be the height of the rectangle. And then the bottom of the rectangle is at y equals 0. So to find the radius of this disk, it's really just the height of this rectangle, which is the difference between the top y coordinate and the bottom y coordinate. So that's just f of x sub I star minus 0, because the y coordinate at the bottom is 0. So that's just pi times f of xi star, minus 0 doesn't do anything, squared delta x. That's the volume of this one disk. What I want to do then, of course, I want to take all the rectangles as I go across from A to B. That would end up giving me a bunch of little disks that would approximate this overall volume up above. And so if I do that, I form the sum of all those disks. So that's what this is, right? There's pi times that f of xi star squared, that's pi r squared times the thickness of the disk. I'm going to add up all the disks as I goes from 1 to n. So that would be all the disks going across the region. But then I want to have the number of disks go to infinity, right? I want each of those little rectangles to get narrower and narrower. So the width of each disk goes to 0. And so this thing, though, is a Riemann sum. And Riemann sums turn into integrals. So to find this limit, I would evaluate the integral from a to b of pi times f of x squared dx. And that's sort of the underlying formula for this. That, of course, is a region that's just snug up against the x-axis. If we go back and look at that here, that formula really only applies when we have this type of situation where the rectangle, one end of the rectangle is on the x-axis, the other end of the rectangle is on a function, and that's what I'm rotating. So if I have this exact kind of region, then that formula is exactly what we're going to want. We may not have that exact type of region. We might have a situation like this, where I've got a top function, y equals f of x, and a bottom function, maybe y equals g of x, and I want to rotate that solid about the x-axis. Now, I didn't draw a picture of that solid here, but we could imagine doing that. It would be a mirror image, so we'd have something like this, and we'd have that mirror down like that, and then something like this, and then we can imagine, drawing circles around and we'd have something like that. So it would be sort of some sort of a, it'd have this slanted sides all the way around, and then there'd be this inner part where it would be sort of sunk in. That sort of obscures a little bit what I want to look at here, so let me get rid of that. But we can always sort of draw what it would look like, if we had it in 3 dimensions there. In this case here, of course, when I rotate this rectangle about the x-axis, I've got a hole there, right? I've got this hole where the rectangle doesn't reach. So when that gets rotated, we say that this makes a washer, not a disc anymore. And to find the volume of the washer, that would essentially, you could think of it as it's the volume of the outer disc minus the volume of this hole. And so to find the volume of the outer disc, I need what I might say is the outer radius. And to find the volume of the hole, I would need the inner radius. And so that's what I've got down here. The volume of one of these washers, it would be the area of the cross section times delta x. But for the area then, I would take the outer circle's area and subtract the inner circle's area. So pi r squared outer minus pi r squared inner. So the pi could be factored out. I've got pi in both places. And the radius here, the outer radius, is just from this y coordinate of f of x to this y coordinate of 0. So the outer radius is just f of x sub I star. And the inner radius would just be then g of x sub I star. And so I square both of those. And that leads to this kind of integral. So if I have a washer, I always just get pi, and then I have the sort of this top squared minus the bottom function squared. And that would allow me to calculate the volume in that sort of situation. Now, a couple things. It gets a little more complicated than this. If I rotate about a line other than the x-axis, that's going to affect how the inner and outer radii are computed. What do I mean by that? Well, if I was rotating this rectangle about a line, for instance, up here, then the outer radius is going to be this distance. Oh, that's messy. And the inner radius would be this distance. And so I would have to know the y-coordinate up at the top and then the y-coordinate here and here. And so to find that distance, whatever this y-coordinate at the top, I'd have to take it and subtract f of x to get the inner radius. And then this y-coordinate at the top minus g of x to get the outer radius. It still would be this formula. But it's not just going to be f of x and g of x now. It's going to be something else. And we'll look at some examples of that in the example problems. But that's one thing to be aware of. These formulas, exactly as they are, only really work if you've got the exact situation we've described, and that's not necessarily true. Also, to get the disc or washer, it's really important that the representative rectangle be perpendicular to the axis of rotation. So here we've been rotating about the x-axis, and my rectangles have been vertical then. So, my x-axis here, if I take a rectangle and rotate about the x-axis, that's where I get this, you know, the rectangle would be doubled like this, and it's being rotated, so I get, you know, it's not as pretty as what I had before. But if I'm rotating around the y-axis, and I want to get a disc or washer, I'm going to have my rectangle oriented this way, so that when I rotate it, you know, I get something like that. So my washers are going to be perpendicular to the axis of rotation. In this case, I don't have a little delta x, I would have a little delta y. And so, you know, if I have vertical rectangles, I have delta x, I'm integrating with respect to x. If I have horizontal rectangles, I have delta y, and I'm integrating with respect to y. And when we look at some example problems, you'll see how that works.